Hello and welcome to this lecture 2 of module 3. Yesterday we were discussing linear equations and we discussed about vector spaces, took a small detour to talk about condition number and other things. What we left out in the previous lecture is what happens when we go from a 2 by 2 system to an n dimensional system where we have n equations and n unknowns. And a typical equation in that particular case will be written in the form of a11 multiplied by x1 plus a12 multiplied by x2 and so on up to a1n multiplied by xn equal to some right hand side term b1, where a11, a12 up to a1n are the coefficients and x1, x2 up to xn are the variables that we are interested in solving the equation for. Likewise, we will have the second equation as a21 x1 plus a22 x2 and so on up to a2n xn equal to b2, and the nth equation of course would be a n1 x1 plus a n2 x2 and so on up to a nn xn equal to bn. Okay. As we have done before, the unknown all the unknowns will be put in a vector form, and that vector is going to be a vector x1 x2 and so on up to xn. This is what we will call as the vector x bar. That is going to be equal to the right hand side. Again it is straightforward that we will get a vector b1 b2 up to bn. Okay. And we will get a matrix A on to the left hand side. This matrix A, the dimension of this matrix A it has to have n number of columns because there are n variables. So, it has to have n number of columns and the number of rows will be equal to the number of equations. In this particular example we have taken n equations in n unknowns. If there were the number of equations were not equal to n, if there were say m number of equations, we will have m number of rows and n number of columns in this matrix A. Now, how do we populate this matrix is this first element 1 element over here is going to multiply with the first variable over here, the second element will multiply with the second variable, the third element will multiply with the third variable and so on. Okay. So, first row will contain all the coefficients in the first equation, the second row will contain the coefficients in the second equation and so on, and the ith column will represent the coefficient of the ith variable in this particular vector. Okay. So, we will have a11, a12 and so on up to a1n as the first row, a21, a22 and so on up to a2n as the second row, and n1, an2 and so on up to ann as the nth row. So, this becomes our n by n matrix A, and this is our matrix representation of the n equations in n unknowns. Of course, when n is going to be equal to 2, we have just these 4 terms a11, a12, a21, a22 and we just have b1 and b2 over here on to the right hand side. Okay. So, this is the overall matrix representation for an n by n system. The next question that we asked ourselves is, when do this system of equations have a unique solution, when does it have no solution and when does it have multiple solutions. And what we had seen in the previous lecture is it has the system of linear equations has a unique solution if rank of A is not equal to 0. What do we mean by the other way of putting rank of A is not equal to 0 is that the determinant of A is non-zero. Okay, both these terms are equivalent, but it is much easier to evaluate a rank of a matrix rather than to evaluate a determinant of a matrix for a large size systems. And in fact, evaluation of a determinant is very computationally intensive, and that is the reason why Kramer's rule, although it looks fairly straightforward to implement, is actually not very useful for any type of practical examples, and that is because the amount of computational effort required in computing a determinant is much larger than that is required for computing say a rank or for solving this set of equations using the numerical methods that we are going to cover in this particular module. Okay. So there will be a unique solution if rank of A is not equal to 0. If rank of A is equal to 0, we can either have no solutions or we can have infinite number of solutions. Okay. If rank of A equal to M, then we will have either 0 solutions or infinite number of solutions. In that particular case, what we had seen in the previous lecture is if each of the columns of the matrix A, if we represent them as vectors, say we represent this guy as vector v1, this guy as vector v2, and so on up to this guy as vector vn, then if b bar can be expressed as a linear combination of these vectors, then there will be infinite number of solutions. If it cannot be represented as a linear combination of these vectors, there will not be any solution. What that translated into in the previous lecture for a 2x2 system was that the rank of matrix obtained by putting A and B together, what we mean by this is that the first n columns contain the n columns of A and the n plus 1th column contain the vector B over here. So this is a new matrix that is formed by horizontally concatenating the matrix with the vector. Now if we create a matrix of this form, if the rank of this matrix is going to be equal to M, as which is the same as what we had over here, then we will have infinite number solution. Rank equal to M, then we have infinite solutions, and if rank of this matrix equal to M plus 1, we have 0 solution. Okay. Why M plus 1? Because we have just added one more column, so the rank cannot actually be greater than M plus 1. The largest rank that this can reach is indeed M plus 1. So if this, so these are the conditions for this the system of equations to have one solution, infinite number of solutions, or 0 solutions. And in this context, would that small detour that we took in the previous lecture talking about vectors and vector spaces and solving the equations in terms of vectors rather than intersection of lines is very instructive, because all these results directly fall out from very lucidly and very simply fall out from explanation in that particular form. So what I will do next is take up the 2-dimensional example, 2 equations and 2 variables that we saw in the previous lecture, try to see how we will naturally solve that example, and try to derive certain points or certain hints on how we solved it and why that particular solution technique worked. Okay, and then we will extend it to an n-dimensional system. So the 2-dimensional example that we took in pretty much the last minute of the previous lecture was x plus 2y equal to 4 and 2x plus 3y equal to 7. Okay, and for this particular example, the matrix notation of this equation is going to be, I will put it in x1 and x2 just to make it more consistent with the notations we are going to use later. So, the two variables are going to be x1 and x2 instead of x and y. Nothing really changes in this equation by changing the variables from x and y to x1 and x2, and I have changed from x and y to x1 and x2 so that extension to an n dimensional system becomes very clear when we actually do that extension. Okay. And then we have the right hand side is going to be 4 and 7, and the A matrix will be 1 2 on the first row and 2 3 on the second row. So, we have 1 2 2 3 on the second row, and in the matrix over here the vector over here is 4 7. Okay. So, this is matrix A, this is X, this is B. Okay. And we will define a concatenated matrix A bar B as nothing but 1 2 4 2 3 7. Okay. So, these are our definitions for now. Okay. Now, the question is, how do we go about solving it, and this is perhaps something that we have been solving from maybe the 7th or the 8th class. So, this type of equation is not very difficult for us to really solve. What we will actually do is we will first try to eliminate x1 or x2 from this equation. In this particular case, it's very clear that eliminating x1 is what we ought to be doing. So, we will write this as equation 2 minus equation 1 multiplied by 2. Okay. So, this is what we are going to do, but instead I will write it in this form plus equation 2 multiplied by plus equation 1 multiplied by minus 2. So, 2x1 minus 2x1 will give us 0, 3x2 minus 4x2 will give us plus negative x2, and 7 minus 8, 2 into 4 is going to give us minus 1. Okay. And so, this will be our new equation. So, this was our equation 1, this was our equation 2, this we call as equation 3. Now, using equation 3 and equation 1 together, we can then solve these equations in order to get the solution. So, of course, the one solution over here is x2 equal to 1, and then back substituting in 1 okay. So, we put x2 equal to 1 over here. So, x1 plus 2 equal to 4 and x1 equal to 2. Okay. And this is how, in a fairly straightforward manner, we have been solving these equations. Okay. So, what we actually did was this: we had equation 1, which let us again go back and think about it from a geometrical perspective. Equation 1 represented a line. So, let me call that L1, which corresponds to x plus 2y equal to 4, and let us talk about the line L2, which corresponds to 2x plus 3y equal to 7. Okay. Now, let us take a linear combination of the line L1 with line L2. Okay. And a linear combination basically means that we are going to take alpha L1 plus beta L2, where alpha and beta are two scalars. Okay. So, let us look at the left hand side of this equation. Is going to be equal to alpha multiplied by x plus 2y, or rather I should use x1 and x2 rather than x plus 2 x and y, plus beta multiplied by 2x1 plus 3x2. Okay. Now the solution of these two equations was the point 2 comma 1, right. So the solution was okay. So let us substitute this particular value in this equation. We will get alpha multiplied by 2 plus 2, that is 4, plus beta multiplied by 4 plus 3, that is 7. Okay. So we have 4 alpha plus 7 beta, or alpha multiplied by 4 plus beta multiplied by 7, that is nothing but the RHS of alpha L1 plus beta L2. So the right hand side of alpha L1 plus beta L2 is going to be alpha times 4 plus beta times 7, which is the same as LHS. So what does it mean? What it means is that the point 2 comma 1, it satisfies the equation L1 and it satisfies the equation L2. That means this particular point lies on the line L1 as well as it lies on the line L2, but it also satisfies the equation alpha L1 plus beta L2, which means that for any scalar values alpha and beta, including alpha equal to 0 or beta equal to 0, the point 2 1 is going to lie on that particular line. So okay. So we are interested in finding out this point, what this point actually is, and since this point also lies on a linear combination of these two line segments, as a result of this we can actually do any type of manipulations of this sort. That means equation 2 plus minus 2 multiplied by equation 1, and the result that we get is still going to pass through the solution of those two lines. And this is not just true for a 2-dimensional system, this will be true for any n-dimensional system. If we have n equations in n unknowns, that is going to represent basically it is going to represent n hypersurfaces, and if we take linear combination of any hypersurfaces amongst those n hypersurfaces, the point of intersection of those hypersurfaces is also going to lie on the linear combination of those hypersurfaces. This linear combination and this property of the vector spaces is really the reason why this idea works of taking equation 2 and subtracting 2 times equation 1 from this equation. Okay. So this is how we did when we tried to solve this set of equations using the methods that we were familiar with. Now let us look at what we actually did so that we can learn some lessons from it and go ahead and try to implement that in the Gauss elimination process. The first part, what we really did is something that we will try to relate to Gauss elimination. The second part that we did is something that we will relate to what is known as back substitution. Okay. So what we did in Gauss elimination is we took the matrix AB, we took the matrix AB over here, okay, and then we subtracted from the second equation 2 times the first equation. So from this particular guy we subtracted 2 multiplied by this guy. Okay. So the AB matrix we had was 1 2 4 and 2 3 7. Okay. From this the two equations that we were left with were these. Okay. So first we had equation 1 and 2. Okay. We did equation 2 plus minus 2 multiplied by equation 1 and we ended up with this equation. If this equation we have to write this in basically a vectorial notation, in a matrix notation, it is going to be 0 multiplied by x1 plus minus 1 multiplied by x2 equal to minus 1. So I will erase this equation and write it in a different way, it is 0 multiplied by x1 plus minus 1 multiplied by x2. So, now what we are left with is we are left with equation number 1 and equation number 3, and we will try to solve equation 1 and 3 together. That is exactly what we did in the back substitution step. Okay. So, equation 1 is 1 2 4 in the matrix A B, and equation 2, if we again go back to this equation number equation number 3 is 0 minus 1 minus 1. Our matrix A is going to consist of 1 2 0 minus 1, our matrix B will consist of 4 minus 1, and when we put those two matrices together, the first row will contain 1 2 4, the second row will contain 0 minus 1 minus 1. Okay. So, what happened is we went from this matrix AB to this new matrix AB, and how did we go ahead and get this particular matrix? This particular matrix we got by taking row 2 and adding minus 2 multiplied by row 1 as row operation. Okay. So, what we are going to do in Gauss elimination is to do the following. Okay. In general, what we are going to do is we will take the jth row, in this particular case the second row, and add to it some coefficient alpha multiplied by the ith row. Ith row in this particular case was first row. So, specifically what we did over here is we did R2 where the j is equal to 2 plus minus 2 multiplied by R1 where I equal to 1. Okay. So, this is what we will do as a row operation in Gauss elimination step. So, what row operation does, it replaces one of those equations from n equations with a linear combination. For example, in the problem that we just solved, what we did was we replaced L2, the line L2, with the line L2 minus 2 times L1. So, we replace the one of the lines with a linear combination of the two lines that we had in the previous equation. So, this is one type of row operation. The second type of row operation is we know that it does not matter whether we call one particular line L1 and L2. Instead of calling this line as L1 and this line as L2, we could have very well called this line as L2 and this line as L1, and it would not have made any difference. That means that by exchanging the two rows, the solution of the overall linear equations also remains the same. So, the other type of row operation possible is exchange of rows. Okay. So, these are the two row operations that we will use such that we get an upper triangular matrix for the matrix A. So, what do we mean by upper triangular matrix for matrix A is that all the values on the diagonal and above diagonal may or may not be zeros, but all the values below the diagonal have to be 0. Okay. So, we will try to get zeros in all the equations. Below equation number 1 we will get zeros for the variable x1, below equation number 2 for all equations we will try to get 0 for the variable x2, so on and so forth. And when we go back and check what we have over here, this is the A part of our matrix and this is the new B part. So, what we have done over here is A itself we have got this as an upper triangular matrix, all the values below the diagonal are 0 in this particular case, and this is our new vector B. Okay. So that is our Gauss elimination step. Using row operations, convert matrix A into a lower triangular matrix. And the same row operations have to be implemented on the vector B as well. Okay. So this is what we will do for doing the Gauss elimination. Okay. Let us look at another example, a 3-dimensional example, and then we will extend it to an n-dimensional system. I am taking the 3-dimensional example and I will use it to explain both Gauss elimination as well as another method called the LU decomposition method. Okay. So let us consider these three equations, these three linear equations in three unknowns. The unknowns are x1, x2 and x3, the coefficients 1, 1, 1, 2, 1, 3, 3, 4 and minus 2. Okay. So this is our three equations in three unknowns. Let us give ourselves about half a minute to think about how to have a matrix representation of this equation and how to have how to solve these particular equations. Okay. Okay. So let us talk about the matrix notation for these particular equations. So we are going to write it in form of Ax equal to B. The matrix A is going to be 1, 1, 1 in the first row. In the second row we will have 2, 1, 3, and in the third row we will have 3, 4, minus 2. For matrix for the vector B we will have 4, 7, 9 as the vector B. Okay. So now we have the matrix A and the vector B, and then we will try to solve these equations using the Gauss elimination process. Before that we will try to solve it using the algebraic method that we typically use. So the first step that we will do is take equation number 2, okay, and add minus 2 multiplied by equation number 1, and we will take equation number 3 and do minus 3 multiplied by equation number 1, okay, and they will give 0 x1 plus 1 minus 2, that is minus 1 x2 plus 3 minus 2, that is x3 plus 1 x3 equal to 7 minus 4, that is 7 minus 8, that is minus 1. We will again have 0 x1 plus 4 minus 3, that is 1 x2 plus minus 2 minus 3, that is plus minus 5 x3 equal to 9 minus 12, that is going to be equal to minus 3. So now one equation is going to be equation number 1, this is going to be our new equation number 2, this is going to be our new equation number 3. Okay. So next what we will do is we will add these two equations and replace the last equation with that particular sum. So we will do this as equation 5 plus 1 multiplied by equation 4, and when we actually do that we will get this as 0 x1 plus 0 x2 plus minus 5 plus 1, that is minus 4 x3 equal to minus 3 minus 1, that is going to be equal to minus 4. So now we have the three equations in three unknowns. The first equation is 0 x1 plus 0 x2 minus 4 x3 equal to minus 4, back substituting we will get x3 equal to 1. Next we will substitute x3 equal to 1 in this particular equation and we will be able to get x2 equal to 2 over here, and x3 equal to 1 and x2 equal to 2 will actually give us x1 into this equation, and that will actually give us x1 equal to x1 equal to 1 in this particular equation. Okay. This is how we go about solving. What I have done so far are the steps that will be involved in getting a lower triangular matrix for the matrix A. Keep in mind the same row operations that we use for the matrix A, we are applying the same row operations for the matrix B as well. So the first point is that Gauss elimination step, when we have n equations in n unknowns, will involve n minus 1 steps. Okay. In each step we have multiple sub steps. Okay. What we will do in ith step, we will use the ith row okay, we will use the ith row to make the coefficients of xi in all equations in row I plus 1 up to row n equal to 0 to obtain okay, we will use ith row to obtain the coefficients a I comma j for where j is greater than I equal to 0. So what we mean by that is the first step is to construct or the 0th step is to construct the matrix AB, which will be 1 1 1 2 1 3 3 2 minus 2 sorry 3 4 minus 2, and our B is 2 7 9. Okay. Step 1 will involve making this and this element as 0. So step 1 is use R1 okay, use R1 to obtain zeros in column 1 in row 2, row 3 and so on up to row n. Okay. So what we will do is R1 or sorry our R2 is going to be our original R2 plus some coefficient alpha 2 1 multiplied by R1, and likewise we will have R3 as R3 plus some coefficient multiplied by R1. Okay. I will write it in this particular form. Okay. So what did we do over here? If we go back to this equation, what we did is we multiplied it with -2, and in the equation 3 we multiplied with -3, and we have multiplied equation 1 with -3 and added that to equation 3. Okay. So what we do over here is we multiply the row 1 with -2, which I will write this as -2 divided by 1, and this I will write this as -3 divided by 1. Okay. And when we do that, the next matrix AB that we will get is we will get 1 0 0 1 1 2 over here. So this will be -2, this term will be 1, this term will be equal to -1. Okay. And this of course is 0, 4 minus 3 is 1, minus 2 minus 3 is -5, and then 9 minus 2 is 1. Okay. And if we compare it with the equations that we got, the new equation was 0 minus 1 1 minus 1, 0 1 minus 5 minus 3. So so we actually do, oh sorry, this should be -1. 0 minus 1 1 minus 1, 0 1 minus 5 1 is actually what we get as our matrix A after the first row operation. Okay. Keep in mind what we have done over here is multiplied this R1 with ratio of coefficients. Okay. So alpha 3 1, because we are changing the row 3 with by using row 1, alpha 3 1 is going to be equal to negative A 3 1 divided by A 1 1. Likewise, what we have over here is alpha 2 1 is going to be negative of 2 divided by 1, which is A 2 1 divided by A 1 1. Okay. So this is what we did as step 1. In step 1 we used row 1 in order to make zeros in all the in the first column below the first row. Okay. So in step 2 we will use the row 2 in order to make the coefficients in column 2 equal to 0 below row 2 using the row operations. So the result of step 1, we had this particular matrix, and in order to make 0 over here we have to multiply with negative of the ratio of the coefficients. So minus 1 divided by minus 1 is what we have to multiply it with. In other words, we just have to add those two equations. So what we have to do is we have to do R3 plus minus 1 divided by minus 1 multiplied by R2. Keep in mind this is ratio of coefficients. Okay. So when we do that, what we will get is we will get 1 1 1 2 in the first row is unchanged, 0 minus 1 1 minus 1, the second row is unchanged. We will get this as 0 0 minus 4 and 0 over here. Okay. So that is what we are actually going to get when we do addition of these two rows. I think I have probably made a mistake over here. So when we do this row operation, this will be 0 minus 1 minus 2 is minus 1, 3 minus 2 is plus 1, 7 minus 4 is plus 3, and 0, 1 minus 5 and 3 times yeah and 1. Okay. So, this is what we have we ought to be getting. So, we will get 0 minus 1 1 3 and 0 0 4 4. Okay. So, this is what we will get. So, in terms of this matrix A that we have over here, this is now reduced to a lower triangular matrix. Okay. And then we will use the back substitution and in the back substitution step we will have x3 going to be equal to 1, we will substitute this x3 equal to 1 over here, x2 equal to minus 2, we substitute x2 equal to minus 2 and x3 equal to 1 over here, and we will get x1 equal to 1 in this particular equation. Okay. So, this is how we will actually get the final solution. So, in back substitution we will use 4x3 equal to 4, which will give us x3 equal to 1, and then we will substitute x3 into this equation, and then we substitute x2 and x3 into this equation, and we get the overall solution. So, Gauss elimination will consist of n minus 1 steps. So, let us say that we have an n by n equations in n unknowns. So, we have the matrix A and the vector B bar, and if instead of one equation, if we had n more, if we had more sets of equation in terms of Ax bar equal to B1 bar and Ax bar equal to B2 bar, we can solve both these equations simultaneously by creating a matrix A B1 B2. So, if we had Ax bar equal to B1 bar as one set of equations and Ax bar equal to B2 bar as other set of equations, and we had to solve this set of equation independently of this set of equations, the way we can go about solving this is create a matrix A B1 B2, okay, and then apply the all the row transformations to this particular matrix, and we will be able to indeed solve this two sets of equations simultaneously. This is going to be very useful when we are going to consider inversion of a matrix, that I am going to consider in the next lecture in this particular module. Okay. So, we have Ax equal to B, step 1 is going to be use R1 to get zeros in column 1, row 2 to n. Okay. And how we do that is Rj is going to be equal to Rj plus alpha j comma I or alpha j comma 1 R1, where alpha j1 is the ratio of the coefficients, and if we go back and look over here, the ratio of the so we had R2 given as R2 plus negative of alpha A21 divided by A11. Okay. Alpha 21 was negative of A21 divided by A11. Likewise, over here alpha 31 was equal to negative of A31 divided by A11. In general, alpha j1 is going to be equal to negative of aj1 divided by A11. Okay. So, this is what we are going to write, aj1 is negative of A j1 divided by A11. Okay. So once we have this particular step, as a result of this step we are going to get, so we will start off with the original matrix A11, A12, A13 up to A1n and then B1, so on and so forth. So our first row remains unchanged, so we will have A11, A12, A13, so on up to A1n, B1. Our second row is going to be, we will get 0 at this location, we do not have to compute that, simply by using aj1 divided by a11 we are going to get 0 over there. So we will have 0 over here, this will be a22 after the first operation, a23 after the first operation and so on up to a2n after the first operation, b2 after the first operation. Likewise we will change our row 3 or row 4 or row 5 and so on. So we will immediately get 0 over here, we will have a32 after the first operation, a33 after the first operation and so on up to a3n after the first operation and b3 after the first operation and so on up to the nth row. Again in the nth row we are going to get 0 over here, okay, and over here we will get a n2 after the first operation, a n3 after the first operation and so on up to a nn after the first operation followed by bn after the first operation. Okay. So this is going to be the step 1 of the Gauss elimination step. In step 2 of the Gauss elimination step we will use row 2 to get zeros in column 2. So that is going to be our next step. Okay. So the step 2 is going to be to use row 2 for row elimination. So we want to get 0 over here, here and so on up to this point, and therefore we are going to multiply rj with an appropriate coefficient multiplied by r2. So rj will be rj plus alpha j2 multiplied by r2, and in this particular case alpha j2 is going to be, for example over here it is going to be negative of a321 divided by a221, negative of a421 divided by a221 and so on up to negative of an21 divided by a221, or in general alpha j2 is going to be equal to negative a j2 divided by a22, okay, and so on up to step I is going to be use ith row for row elimination, okay. So r I plus 1 is going to be equal to r I plus 1 plus alpha I plus 1 comma I r I, where alpha I plus 1 comma I is going to be equal to minus a I minus 1 I plus 1 comma I divided by a I minus 1 I comma I, because this has been obtained after I minus 1 row operations. In fact we will have 1 as a superscript over here, and we do this for I plus 1, we do this for I plus 2 and so on. So we can replace this I plus 1 with just j over here, and so all the I plus 1s will replace by j. So this is what we end up doing. Now if we consider this what we do in step 2 and what we do in step I, we have Rj over here where j is going to be greater than 2, in this case j is going to be greater than I. Okay. So let me write the algorithm okay, and again I am going to very roughly write the algorithm, not in a standard form. Okay, so we will do let I go from 1 to n minus 1, because we are doing those row operations using row 1, row 2, row 3 up to row n minus 1. We are not using the row n minus 1th row to do any row operation. So which means in step I for is going to involve for j going from 1 from j going from I plus 1 to n, that means the row I plus 1, row I plus 2, row I plus 3 and so on, we need to get Rj, or we need to replace Rj with Rj plus alpha j comma I Ri, where alpha j comma I is going to be equal to negative a j comma I divided by a I. Okay. So that is what we have in the ith step. Keep in mind this is not one single operation, but this itself involves multiple operations. So if we were to expand this operation, we will have, so Rj is the jth row. Okay. In the jth row, for the first column we will have it 0, second column we will have 0 and so on up to the j minus 1th column we will have 0. In the jth column we will definitely get 0, because we are using Rj to make that particular in the ith column we will definitely get a 0, because we are using Ri in order to get 0 in that column. So we will have for k going from I plus 1 to n plus 1, where the n plus 1 is for the bth for the vector b. Okay. In this particular case we will have a, so we are looking at the jth row, okay, and all the columns after the column I. So we will go for a j comma k is going to be equal to a j k plus alpha j I multiplied by a. So it is the ith row, so we will have it is the jth row, so we will have so I am sorry, we are going to use the ith row in order to make zeros in the jth row ith column, and this will change all the other columns as well. So this is going to be a I comma k, okay, because this is going to be the column kth, the kth column, and we are going to use the row I in order to change that particular variable. So this is very roughly what algorithm we are going to follow. Okay. So what we have covered so far essentially is the background behind the Gauss elimination, and very briefly looked at the algorithm for Gauss elimination. In the next lecture I will take off from the algorithm for Gauss elimination and try to compute how much amount of computational effort the Gauss elimination step is going to require. Next I am going to talk about the back substitution itself, and finally I will finish off with two other methods, specifically the Gauss-Jordan method and LU decomposition. So that is basically what we will cover in the next lecture of this module. Okay, thank you.